It is time. Thanks for being here, everyone. I am honored to close out RailsConf 2022 with this talk. We'll be talking about a Rails developer's guide to the Ruby VM. My name is Maple. As you know, Ruby powers Ruby on Rails. So I think it'll be worth your while to learn a thing or two about how Ruby works, because it's fun and interesting. So let's begin. OK, so bear with me for just 1 second. What is the difference between a compiled and interpreted programming language? When we say compiled, we think of a translation of the source code into a different programming language. So a prime example is when you write C code, and then you compile it, and it turns into machine code, and that can be executed by the computer. Interpreted language just takes the source code and executes it directly. So when I first started learning about Ruby internals, I was very confused because people were talking about a Ruby compiler, but Ruby is interpreted according to this Wikipedia page that we have. That means it's facts, right? So today we'll be talking about how Ruby is technically an interpreted programming language, but we'll also learn about the nuances of how it is not. So hello again. My name is Maple Ong, or Maple if you're French. Sorry, my team's over there, and sort of an inside joke. But I work on Shopify on the Ruby on Rails infrastructure team. This is our team picture from our onsite in London less than a month ago. This is me in the picture, and we're hiring people who want to work on Shopify or Ruby or Rails. So please go check out our booth if you haven't already, or you can talk to me. So this is the outline of the talk, so you know what to expect. First, we're going to go through the Ruby execution process. End to end, we'll chat about how Ruby does things and use an example code. We'll talk about what is Yarv, how the Ruby VM works, why we care about that, and some practical uses to Rails applications. All right, so this is kind of the overview of the entire process. The first thing that happens when you run a Ruby file is that it gets tokenized. So remember, the computer is dumb in a way that it doesn't understand or read code like you and I do. So it only sees a stream of characters and does not understand it. So we want to break up the stream of characters into the smallest possible element of a source code, in this case, a Ruby file. And it can be broken up into stuff like keywords, identifiers, and symbols. Another word for tokenize is lexical analysis, if you can get fancy. So let's use this as our running example. It is a foo method that takes in 2 arguments, A and B, and it prints the sum of the 2 arguments. And then we call foo with 9 and 8. Because I don't know about you, I can't do mental math, so this is going to be really helpful for me. Let's put this source code into a variable. And let's take a look at how Ruby tokenizes under the hood. And to do that, we're going to use Ripper, which is part of Ruby's standard library. So it is kind of an interface on top of the Ruby parser, and it allows us to use the same tokenization code that Ruby uses and give us an insight on how Ruby does things. And then we'll be calling the method lex, which just short for lexical analysis. So this is the output. Don't feel intimidated. It's just an array of tokens. Let's just zoom in into the first bit, which is the method definition. So this is the method definition. And I want you to kind of notice that the tokenizer actually broke up the method name foo, the arguments A and B, and then also the parentheses. Let's just zoom in some more into one specific token, so the first one. You can also see that Ruby kind of gives us more information about the token. So in this case, like the line number, the column number, the token type. In this case, it's a keyword because def is a keyword in Ruby. And the lexeme, which is just to describe how the token appears in source code. And finally, the token state, which is just the information about the state of the tokenizer when the token was parsed. All right, so this is the overview. So input to the tokenizer is a bunch of Ruby code. And remember, it's just streams of characters. And then the output is an array of tokens. Now that we have those information, the next stage is to parse these tokens. So the structure you see here is essentially a huge chunk of array and kind of incoherent. As I said, the computer doesn't understand, so we need some way to make sense of these tokens. And the goal of parsing is to transform this flat array into more of a tree structure by taking into account stuff like operator precedents and methods, all based on Ruby's grammatical rules. So let's take a look again at how Ruby would do it. Back to our foo example, we're going to use Ripper, the Ripper library again. This time, we're going to use the method sexup. Sorry, we had a whole conversation about how to pronounce this. So is it sexup or sup? I don't know. Let's go with sexup, which refers to S expression, and hence my confusion, right? Like sup, S expression, right? So anyway, or symbolic expression. So S stands for symbolic. And it's just a term used to describe nested arrays or array of arrays, essentially like a tree data structure represented in arrays. So we run this code. This is the output of Ripper sup. As you can see the shape of it. It's nested arrays. So let's zoom in into one single line, the put instruction. And you can kind of take a look at how nested, like command, the identifier, which is puts. I'll do you one better and represent this information in a tree structure. So on the left, we have the sexup representation, and on the right, we have the abstract syntax tree representation of the same data. And that's actually how Ruby stores AST nodes in sort of a linked list structure. All right, so that is the parser, input tokens, output AST nodes. And this is how the parser fits into where we're currently at in the Ruby execution process. So I just want to point out that the tokenizer and parser here are depicted as separate processes just for simplicity, but in real life Ruby, the tokenizer and parser kind of work together at the same time. So the parser has access to the tokenizer, and whenever it needs a new token, it just requests for more. But yeah, just fun facts. So we're kind of at a crossroad here for the third stage. It can go one of two ways. So the first way is that we use these AST nodes and then interpret it directly, which means we iterate over the AST nodes using an AST walking interpreter and then interpret it. So that's kind of the end. And that's actually how Ruby worked before version 1.8. Your Ruby source code will be tokenized, parsed, and then just interpret it. That's it. The other way is to translate, again, these AST nodes into something different using a compiler. So this is actually the Ruby we know of today, and that's how it works. So the third step is actually to compile it. So in Ruby versions 1.9 and higher, we now have a built-in compiler. Just for comparison, a compiler you may be familiar with is the Java compiler. And the Java compiler performs bytecode compilation as a separate and manual step ahead of time. So you have to compile it yourself. But for Ruby, it does it automatically for you, super magical. So you don't have to worry about it. You probably don't even think about it. So the input to a compiler are AST nodes. And the output is something we call bytecode. So bytecode is low-level code that isn't native machine code, so not binary. But it's still easier for the computer to execute compared to a higher-level code. So we're going to take a look at bytecode in just a second. All right, so now we'll take a look at how Ruby compiles our source code. And this time, we're going to use Ruby VM instruction sequence. It's a library similar to Ripper. And we're going to use the compile method and then turn it into an array using 2a. So I've also added these options to compile to just make the bytecode instructions simple, but you don't have to worry about it for now. Anyway, we run this. This is the output. Yeah, it's meant to look like that because it's kind of unreadable without using documentation. So let's try something else and use this method called disassemb, which disassembles the compiled instructions into something more human readable. So this is the output. Better than before. We'll step through these bytecodes in more detail later, so don't feel overwhelmed trying to read it. But what I want to point out to you is that there are actually 2 snippets of bytecode here. And the reason for that is that we have 2 scopes in our source code. So the first one is the main scope, where the method is defined and then called. And this is the bytecode for it. And then the method scope, which is containing the method body, which is just the puts a plus b. Something interesting to note here is that compiling the same program, or in our case, a Rails application, will always result in the same bytecode instructions. So let's just plant that seed in your mind. All right, so this is the compiler, right? Input AST notes, output bytecode. So this is where the compiler fits into the entire process. And finally, we have the interpret phase, where we take the bytecode and interpret them. And we do that by using something we call a virtual machine, or the VM, which is probably what you're here for. A virtual machine is a software that emulates a computer system. Similar to when you run Ubuntu VirtualBox VM on your Mac OS, think of it as an abstraction layer on top of your computer hardware. However, in this context, obviously, instead of emulating an OS, we're actually using this VM to interpret the bytecode. So once the VM interprets the bytecode, that's kind of the end of the entire Ruby execution process. All right, so let's dive into the VM a bit. So if you work on Rails or Ruby, you probably have heard of YARV. It stands for yet another Ruby virtual machine. So YARV is the name for the Ruby VM. And historically, there were many virtual machines created for Ruby, and YARV was the one that just made the cut. And it was created by Koichi Sasada and was merged back in 2007, the same time the compiler was merged. So now that we have an idea of what a VM is, how does YARV work, or how does the Ruby VM work? So the first thing you gotta know is that YARV is a stack-based virtual machine. And what that means is that YARV uses a stack data structure to store values in memory. So in particular, YARV maintains 2 stacks. The first one is an internal stack, and the second one is a control frame stack. So the internal stack stores values such as returns, local variables, and arguments. And the control frame stack tracks Ruby's call stack, so we know the scope of the bytecode that's being executed. When we enter a new scope, so for example, when a method is called or a block is called, a new control frame structure is pushed onto this control frame stack. But we won't go into detail about the second stack here. We won't talk about the control frame, but we will talk about the internal stack. All right, let's go back to our example. But just to keep it simple, let's use puts 9 plus 8 to introduce you to how YARV works. Here, we're just kind of running the same code, so using Ruby VM instruction sequence, the same library we used before, and we're gonna put puts 9 plus 8 as the source code, and then we're gonna disassemble it, and that's the output. So I simplified it, so it's just easier to read. But you can see that each instruction looks like a method call, which is kind of how the VM sees it. You can also visually map the bytecode to the source code. So for example, the send puts command can be mapped to puts, and send plus is like the plus method. So essentially, YARV is gonna just take these bytecode and iterate through it. And let's just take a look at how YARV does it. All right, so on the left, we have the same bytecode instructions, or YARV instruction sequence. And then on the right, you have the internal stack. And we have a stack pointer to manage, to tell us where we are in the stack. And what we want to do first is to have a program counter that keeps track of where we are in the instruction sequence, so what bytecode instruction we're currently executing. So the first one is put self, and this instruction just pushes self onto the stack. Very similarly, put object 9 is an instruction that just pushes 9 onto the stack, and then 8. And when we get to send, so send, we know that the method we want to send is an add or a plus, and then the argc, or the argument count, is 1. So in Ruby, we always have a receiver. So what we want to do now is pop 2 objects off the stack. One is the receiver, and one is the argument. So in this case, 1, so 2 in total. Pop 2 items, so that's 8 and 9. And then we execute it and push 17 back onto the stack. And that's what I mean when I say Yarv uses this stack to manage the values. All right, moving on. Similarly, we have a send puts instruction. And as you know, argument count is 1 and 1 receiver, so total 2. So we pop 2 objects off the stack, execute our puts. And this is when Yarv would print something on the console. And puts would return nil, so we push nil back onto the stack. And then finally, we have leave, which is an instruction similar to return. So it tells us that it's the end of the instruction sequence. All right. Oh, sorry. I hope you're excited, because now we're going to move on to a more complicated example. So as I've alluded to, there are 2 Yarv code snippets here. So one for the main scope and one for the method foo. So let's take a look at the main scope first. So this is the bytecode for the main scope, and I'm going to simplify it. And as you can see, we can kind of map define method foo to the method definition foo in the source code, and put object 9 and 8, and then send foo with 2 argument counts, which is 9 and 8. All right, let's step through it. So the first thing is define method foo, which registers foo in the method lookup table. And then we kind of do the same thing as before, which is put self. So we push self and put object 9, which pushes 9 onto the stack. And then 8. So this is where it gets interesting. So this send instruction is to the method foo with 2 argument counts. So Yarv will know that this is a user-defined method, so something we've written down in Ruby code. Compared to the methods we've used previously, which is puts or add, and both of those are Ruby built-in methods. So once Yarv sees this, we start executing the bytecode instructions for the method scope. So let's take a look at that. So I mean, I don't know if you can tell, but there's actually additional information in this method scope here for foo that I want to point out. So the first thing is that the compiler who generated this information is telling us some information about what arguments this method is accepting. So you can see the size is 2 because we have 2 arguments and 2 argument counts. But in that array, there's also like different types of arguments. So as you know, arguments in Ruby is kind of complex. For example, we need special handling for like block arguments, splat arrays, optionals, keyword arguments, keyword rest arguments. And so this information that we have here will help Yarv eventually do special handling when executing this method. And then the other thing I want to point out to you is this local table over here. It has an index of the local variables of the method. So in this case, we only have 2 arguments, A and B. But yeah, so this is the simplified version of what I just said. Instead of put object 9, I want to draw your attention to get local A and get local B here. So now that we're in a method scope, we're not just putting 9 and 8, we're actually calling a local, or in this case, an argument, A and B. So what getLocal does is it figures out where or what values A and B are, and pushes it onto the stack. So let's take a look at how it does it. So first thing I want to point out to you is that you can see that there are already values on the internal stack. And that is because the internal stack is just one giant stack, and it's managed by pointers. So we want these values to be on a stack because our local arguments values are stored there. So the first thing we want to do in a method scope is push 3 very special variables onto the stack. These special variables store information about the context of the scope we're executing in. But don't worry about it. For now, it's just accuracy that I'm including it. And then we also have something we call the environment pointer, or EP. The environment pointer points to where the environment context begins, so where the special variables begin. And we also use the EP to figure out where, find the local variables when we need it. So in this case, the arguments for the scope that we're in. Again, don't worry about the EP so much. All right, so let's start executing. The first one's put self, and then get local A at index 0. And this is when Yarv will figure out that A is actually 9, so we push 9 onto the stack. And then similarly with B, and then plus. Sorry, this is something you've already seen, essentially. And this is puts, and then we leave. All right, that was very long-winded, but why do we, as Rails developers, care about the VM? Why use a virtual machine in Ruby? We could just execute the AST nodes and just end there. So the first reason is because of performance. It takes extra time to compile, yes, because it is an additional step, but the compilation time pays off if the Ruby program runs long enough. So for example, if there's a loop with a large number of iterations. Secondly, there's also additional optimizations that we can perform on bytecode that we previously cannot do with AST nodes because bytecode is linear. And it's easier to iterate and modify it compared to AST nodes, which is a tree structure. Having a VM also makes Ruby more expandable and future-proof. And we'll talk about JITs in just a second, but it kind of opens up more avenues for future performance improvements. And one example of that is through a JIT. And lastly, remember how I mentioned that the same source code will always be compiled to the same bytecode? And we know what to do when there's data that can be reused. We cache it. So what we can do is cache the bytecode instructions to be used at a later time. And I'll also talk about that in just a second. So the first thing is JITs. How do JITs fit into the Ruby execution process? So JITs, or just-in-time compilers, use the bytecode generated by the VM bytecode generated by the compiler, and work with the VM to translate that bytecode directly into specialized native machine code to be executed directly by the computer. So because just-in-time compilers work just in time, it is able to make smart decisions based on the program runtime information, like types or how often a program takes this specific path, and create specialized machine code for those paths that are frequently used. And that results, obviously, in a faster runtime overall. And the possibility of creating this JIT for better performance for Ruby relies on the fact that there is a compiler and VM existing to create those bytecodes. Theoretically, it is possible to have a JIT compiler for AST nodes, but it doesn't seem like it's very common. So we already have 2 JITs in Ruby. The first one is mJIT, which works by leveraging the C compiler. It's sort of like generating a C extension at runtime. And you can try out mJIT by using the flag --JIT. And similarly, we also have yJIT, which is created at Shopify, and it was recently merged in Ruby 3.1. And we can use that by using the flag yJIT. So you should try it out. It's pretty cool. And maybe do like benchmarks on it, which I think is really cool too. So one of the common woes we share as developers is kind of the wait time for an app to boot. Introducing Boot Snap, which is a gem that makes your Rails application boot snappily, or snappy. You may already have heard of Boot Snap or are currently using it. But now you kind of have a better idea of how it works. But essentially, among other caching optimizations, one of them is that Bootsnap pre-compiles your Rails application and then cache it. So you can save time booting your Rails application locally or in test production environments because it's already cached. All right, so we're in the home stretch here. What are some takeaways that I want you to remember after this talk? The first thing is that the Ruby execution process involves both compilation and interpretation. So even though Ruby is considered an interpreted language, we now have kind of more information about how that isn't exactly the case. So we have AST nodes that are compiled into bytecode, and then the bytecode is interpreted by Yarv. The next thing is that the Ruby VM makes Ruby performant. So having a Ruby VM and compiler makes Ruby, and in turn Rails, run faster. And plus, we can cache the instructions to be used at a later time using gems like Bootsnap. And lastly, the Ruby VM makes Ruby a more future-proof programming language. As I said, it opens up more avenues for future performance. It increases through JITs, and who knows what we can do in the future using the bytecode. So if this sort of stuff interests you, I highly recommend getting involved in one of some education type open source projects. Why bother? It's because I think it's fun and cool when I learned it. But also getting involved in Ruby will kind of drive the development of Ruby on Rails in turn. And it's a great way to get your foot in the door for open source contributions if you're interested in that. All right, so here are some projects I highly recommend. I'm going to walk through them. So the first one is Ruby parser and formatter, or syntax tree. So syntax tree is kind of like Ripper, which is the first library we used. It's a tool built on top of the Ruby parser. And you can either use it or contribute to it. I believe there are issues open. You can use it to build like Ruby formatters or language servers. So for example, our team is using syntax tree to build a Ruby LSP. So I think that's pretty cool. Next one is a Yarv emulator. So by the way, all these projects are written in Ruby. So it will be easy to read and understand and experiment with. So Yarv emulator is actually a project, a Hack Days project we just worked on last week. It was championed by Kevin Newton. And we essentially implemented the Yarv instructions that you saw in Ruby and documented it. So if you're curious about how any of those instructions work, and there are way more than the ones that I just showed, you can check out the documentation. But yeah, that's pretty fun. It's still like a new project, so PRs appreciated. So next one is JIT for Ruby, or Rhizome. So Chris essentially, it's an educational JIT project written out by Chris Seaton, and to teach more advanced JIT compiler concepts if you're interested in that. And like, for example, how types of optimizations a JIT does. And finally, we have Tenderlove's TenderJIT. It's a JIT written in Ruby, for Ruby, and and it mirrors how YJIT works. So if you're curious about how YJIT works, but don't want to read Rust code, you check out TenderJIT. And finally, I've included YJIT and Bootsnap because I've mentioned it. But that is all. Thank you so much for having me. I hope you enjoyed the talk.